All right, everyone, welcome to the stream. The poll came back for a recovery and evacuation conversation today, and that is going to be our primary focus. Whatever questions you have in terms of the recovery procedures, if you have any questions on evacuation procedures, that is the focus of today. And this is true for any type of chillers. So it doesn't matter if you're dealing with air cooled scroll, reciprocating, water cooled centrifugal, whatever the case may be. It's all of those are on the table. And part of the idea behind these is to kind of give us some more focused time with every stream we've done so far. And I know this from just years of teaching classes. If we don't get specific enough with our topic ahead of time, it's just not possible to effectively cram it all in. So it also makes it easier for me on a presentation scale to have a more specific topic, because then we can get into stuff like this, and I can show you more relevant examples efficiently, right? If I was trying to do that without a more specific, like let's go this direction, wouldn't be able to present that quite the same. So we are live, we are rolling. I hope everybody is having a wonderful day, wonderful week. Hope you had a great weekend. With that, yeah, this first question is already lined up. I get this all the time, and that's okay. Like, this is a great conversation to have, and it's something that I had to learn through the field and just working with different mentors over time. It wasn't even something I picked up in trade school. So it's a big question. Is push-pull or standard recovery better? The short answer to that is it depends on your situation. In some cases, you may not be able to use the standard or the push-pull recovery method. And then all that leaves you with is like a standard type of recovery. And by standard here, I would define that as like direct recovery. Okay, so in a lot of the material I write and I talk about, I'll say push, pull, or direct instead of standard. But standard isn't a bad way to say it. I've taken to using the term direct just to give it a little more distinction. So, what are the differences between those? It changes how we are using the refrigerant to move itself with a recovery machine. That's a very vague, kind of weird answer. So essentially with direct, that is a traditional style of recovery. Okay, so when we are, this would be an example of a push-pull you're seeing here. Let me grab a direct. I think, yes. Okay, so this would be an example of a direct. In this particular example, we're using a G5 twin, and we are pulling off of this tank and just pushing directly into our chiller. And now this particular case we're charging. It doesn't really matter whether this is charging or recovering. And if you didn't know, you can use recovery for charging. We can talk about that more in a few, but that's just in case you hadn't been presented with that type of theory or thought process before. It's an extremely effective way to quickly get the charge in the machine and get the complete charge and not have to do the whole suction charge thing like you would think about if you had only done light commercial residential type work. That's not really something we consider. At least that was never something I learned until I got into the heavy side. Well, you use it to pull the refrigerant out. Why not put it back in? That's a good idea. Anyway, so right here we're charging. And this will be what I would consider direct. It's coming straight out of the tank into the machine and then into the chiller. Now a push-pull configuration. And there's lots of things to judge in this picture. That's okay. We're going to focus on what we got set up here. This would be a push-pull. So what we've got going is this is a York YK centrifugal. Our liquid charging port is down here at the bottom. and it is coming up into this cylinder here. And then I am charging in this particular case. I had to sit there and think about it. There's a vapor port right here behind this recovery machine. So what I've done is I've connected a line from that vapor port into the recovery, coming out of the recovery and going into this first cylinder on the vapor line, coming out of the vapor or out of the liquid line, going into the next tank. Now you don't have to do this whole series thing, okay? So let's just ignore this part for now. And let's just simplify this too. We're pulling vapor out of the chiller. We're pushing that vapor into our tank, and then that tank is pushing the liquid out the bottom through the dip tube back into the chiller through its liquid. So this would be an example of a push-pull. Now, to recover or charge, you just flip the hoses the other way, right? So in the direct recovery example, your outlet of the recovery machine goes to the tank instead of to the chiller, right? And in this particular case, if we were to do a recovery, instead of pulling vapor from the from the chiller, we would pull vapor from the recovery cylinder. And then we would push the vapor into the chiller to push the liquid out. And that's where the whole push-pull comes from. That's the whole concept. We are pulling here and then pushing that, specifically vapor. Okay, so as we do this to help us minimize or maximize our ability to manipulate how the refrigerant flows. So with a recovery machine, our speed of recovery or charging depends on the pressure differential across our pump. So the lower we can keep that differential, the less the pump has to work to move the refrigerant, the smoother we can transfer that refrigerant. That's what we're doing in the end. We're just transferring from one place to another, whether it be into the cylinder or out of the cylinder. So by using push-pull, its objective is to just move the liquid refrigerant. Now, one of the caveats to push-pull is you still end up having to do a standard recovery process. The difference is you're only having to do it on the vapor that's left either in the chiller or in the recovery cylinder, depending on your circumstances. So why would we go through all that extra work to begin with? It's because it is faster. I've done several tests with this over the years, and I can move probably about twice as much refrigerant in the same amount of time. It takes about half the time if I can do a proper push-pull configuration compared to what it would take if I was running a standard direct recovery. And that's including, I'm one that, it depends on the recovery machine. You can't do this with all of them, but some of them you can move liquid through them. Not all of them. I want to really big caveat that here. Not all. So the ones that you can, I'm a proponent for utilizing that feature. You can safely move liquid through them if you do it correctly. Okay, so I don't want to get too far off on that tangent, but that's a very fast way to move refrigerant in a direct situation where your recovery machine is literally just pumping the liquid from one place to the other to maximize the flow rates. So doing that procedure and comparing that type of procedure to a push-pull, the push-pull is still about twice as fast. So yeah, that is my preferred, so if I have that as an option, so why would that not always be an option? Well, for push-pull to work for recovery specifically, you have to have your liquid refrigerant consolidated into a single space. So we have lots of chillers that the refrigerant may consolidate, but we don't have an access port. I'll give a perfect example. A York YVAA, or even a YCIV as far as that goes, but especially the YVAA. The YVAA stacks the majority of its refrigerant in the evaporator at shutdown. And it's got, I mean, it's a perfect flooded evaporator. It's not even a DX style like the YCIV was. So all we need is just a port to pull from. And they give us this little dinky 1/4-inch port down by the filter dryer for where the adductor is. But I mean, come on. So when you're doing a YVAA, you end up having to do just a direct recovery on the entire circuit. That's been really the only legitimate way that me and anybody I've talked to has been able to do that recovery. There's just not, without adding a valve somewhere, there's not a way to do a push-pull because we don't have access to the consolidated liquid refrigerant, because that is what makes push-pull so valuable. The ability to move a large volume quickly of that liquid refrigerant, because the liquid is what kills your transfer times, not the vapor. The vapor really doesn't take that long if that's all that's there. But when you've got pockets of liquid scattered throughout the machine and you're having to boil all that liquid off in order to do the recovery, which is what a standard recovery would end up being, it takes freaking forever. So if it is an option, push-pull will save you time. It just depends on the circumstances. So if you have that, use it. If you don't, standard's all you have. So as to which is better, that's the way I see it. Let's see, microboard. Yeah, we are focused on recovery and evacuation today as much as we can. Do you use a CPS MT69 or other tool to reduce the pressure? And the MT69, I'm pretty confident that is the model number for their subcooler, where they call their molecular, molecular transmitter or something like that. They've got some fancy name for it. Here, I want to verify. I'm pretty sure you're talking about their subcooler. Let me check for you here. Yeah, okay, all right. Do you use the CPS MT69 or other tool to reduce pressure? Yes, those are absolutely good and valid tools to have. Now, specifically the CPS version, I don't care for their design specifically. The reason for that is it's too compact and small for large volumes that we transfer. So what this is, it's a subcooler. They've got a fancy scientific technical name or something for it, but we refer to these as subcoolers in the industry. I've made my own. I've got a few different versions of it I've made. So I came up with a design for a braze plate one. Now, I'm not the first person in the world to ever come up with that. And I've had a few people take that design and iterate it for themselves as well. And so having a subcooler is extremely important, especially if you're doing an outside recovery of any kind on a high pressure refrigerant. You really want some way to be able to de-superheat that refrigerant. And we call it subcoolers or subcooling because we technically do get it to, or at least the good ones will get it back into a liquid state lots of the time. Really, the main objective is to de-superheat the heat of compression that is added with through the recovery machine, and then compressing more and more refrigerant into the recovery cylinder that we're using. Like, that is our ultimate issue. Recovery cylinder, between not only just cramming more refrigerant into that same space, but then the heat of compression we get from the recovery pump. Those two things cause a lot of pressure and heat to build up in our cylinder. that slows down, if not brings our recovery to a complete stop in some cases. So people over time have used water hoses on the tanks. I mean, I've done that plenty of times. There's several methods we've tried to use. So a subcooler is an extremely effective way of being able to de-superheat that refrigerant, so that we don't allow that heat to stack on our cylinder, and we keep our tank pressure down, which means we move more refrigerant faster. So my issue with CPS's design is moving large volumes in a chiller application. It's too tightly wound. So when we make our own, typically what you'll do is you'll take a nitrogen, little 30 cubic inch or cubic foot nitrogen tank, something like that, and you'll use that, and you can wind 15, 20 feet worth of 3/8 copper around it, and give you 2 stub outs, stick that in a 5-gallon bucket. You've got a subcooler. That was my very first one I came up with. So the benefit to a setup like that is the copper coils get spread out a lot further. It's not as compact, and it's not in this nice, neat, pretty package. And if all you're doing is smaller equipment, that little CPS one is great for that. My issues I've had is it struggles to keep up with high volumes over an extended period of time, which is what we're doing when we're doing a chiller recovery. Like, we're moving hundreds of pounds, and this would be in an air-cooled application specifically. So even if you're trying to use this on a larger water-cooled, it's not big enough. It's not adequate for that type of application. So that's where, in my opinion, creating your own out of just a copper coil is probably better. You get better operation out of it. Then you just have to deal with, do you use ice? Do you have an ability to just constantly have water cycling through your bucket? How are you going to cool it? And that's where I liked the braze plate version I came up with, where we can flow water through the braze plate, and then the water flowing through there on one circuit, refrigerant on the other circuit, works extremely well. And then I'll take and connect I've got a nylon tube with a barb fitting I'll stick onto it, and I can run that to a drain somewhere, whether it be a roof drain, a floor drain. I can get that into a drain. It doesn't take a ton of water, just a pretty steady trickle, but it's enough that it can remove that heat out of it that we need for the de-superheating. So, do I use the CPS tool? No. Have I? Yes, plenty. I've had some companies that provided that as a company provided tool, I guess. But I'm not a fan, and I wouldn't buy one at this point for our work. Okay, if you're doing smaller stuff, it's probably going to be fine, but not for our work. So why don't I'll hit this one real quick. So this one is kind of adjacent to what we're talking about. Okay. Explain a purge unit in simple words. A purge unit is on a low pressure machine. It is used to remove non-condensables of whatever kind out of the chiller. With low pressure, we operate in a vacuum below atmosphere. That non-condensables can get in through just general leaks, right? It's just one way. However they get in, the purge is able to separate those. It separates them by making the refrigerant condense, because it is a condensable. And the non-condensables, whether it be moisture, air, those won't condense because they're non-condensable, right? Very simple terms here. And so when they separate, the refrigerant is able to go back into the chiller, and then we're able to use a little pump that can suck the non-condensables off of or out of its a little chamber that it stacks all this in. It can, and that's how it can remove those non-condensables. Now, let's take this a step further and bring it into relevancy on the recovery side. If you're doing a low pressure recovery, something to consider is having and they make these. So Ref Tech, they have a portable purge unit that you can hook up and use during a low pressure recovery. So if you've got a machine that has, and this is just a good safe procedure to do, whether you think you have non-condensable issues or not. During the recovery phase, there is a lot of opportunity for non-condensables to get into the system, and we aren't going to want that in there, especially if we're going to reuse that refrigerant later to get that machine back online. And we don't want to be in a position to where at startup we're trying to mitigate non-condensables in the system that may have just happened during the transfer phase of things. So using a purge unit during recovery or even on your recovery cylinders can or is a very good procedure to have. So that is something I would recommend you consider. Is if you can make your own. I've seen versions of where guys have made their own, but you can also purchase a ready built package through somebody like Ref Tech. Like I said, they've got one on their site. I've heard a lot of good things about it. I haven't personally used theirs, but I do believe in Ref Tech and their quality and their tools and what they do. So I'd highly suggest you consider that. So if you're doing a lot of low pressure work, that is something to look into. And at one time, it was something that was a fairly standard practice, because a purge trying to many parts of the world, these centrifugals will go through a shutdown period and they'll be off for months at a time. Not everywhere. In my particular region, we don't have much time down. We run just about year round, and in some applications, it genuinely year round. So we just never see those off cycles. But there are a lot of, say, northern or upper parts of the hemispheres, how about that do have pretty heavy shutdown cycles. During that time, those purge units aren't really going to keep up with non-condensables in the system, not the way that they need to. And so sometimes having a portable purge, you can come in as a part of your maintenance procedure or your annual startups and let that purge run on that chiller for a little while before you try to do a startup and then immediately go into surging issues due to the non-condensables that happened over the off season. Like, again, just some of the things to think about and consider, and how having a portable purge is a really effective, and if you're doing a lot of low pressure work, a needed aspect of your toolkit. Aha, this is a good question. Okay. Do you separate oil from freon during recovery? Now, but by freon, let's just say refrigerant, okay? The freon is specific to like a brand name almost. Anyway, separate them. So we can't directly separate them during the recovery phase. So if we have a machine that had a heavy oil migration, or was having oil stack in the evaporator, which is it's a fairly common thing we have to deal with. So in the event that happened and the refrigerant you took out was very oil latent, the process of doing that, there's two lines of thought that I have seen. I'm in terms of if I had to pick one, I think I like the second one better. Let's talk about the first one. Okay. You're going to go through the full recovery, and when you're done with the recovery process, you're all of that oil is going to have mixed with the refrigerant just in the process on its own, right? And that oil is going to settle at the top of the refrigerant level. So the oil is going to sit up on top of the refrigerant. If you're doing a once you get ready to go back to charging that refrigerant, you either have to pull vapor off, vaporize that entire charge back into the machine. So you won't charge liquid back, you would charge vapor back. In some cases, we've if we are worried about oil contamination in each tank, what we've done is we'll recover down until we know we've got just a few inches or maybe a foot left in the bottom of the cylinder, and then pull that back off of vapor. That way, whatever oil may have stacked on top, we can try to make sure that we get that vaporized, or the refrigerant vaporized back out of it, because the oil is going to stay in its oil liquid state, but we can flash the vapor out, or the refrigerant out into a vapor, and still get the refrigerant back out of that oil. And that is one way to separate those. So a clever thing I heard about recently was waiting until the last. If you have an idea of what your charge should be, waiting until the last, say, 100 pounds or so, the last little bit of charge is left in the refrigerant, basically enough that should fit into one single tank, and then intentionally recover that portion of the charge, of the liquid charge, into that tank. So instead of kind of just haphazardly doing it, which is probably more of what I have done more of, and then having to try to mitigate it later, instead trying to focus that oil latent refrigerant into a single cylinder. Then you can charge your other cylinders accordingly, and not have to worry about it as much. But that last cylinder that everything got stacked into, that should be your oil latent cylinder, you get back into the only way to get those two apart from each other is to flash that refrigerant out of there, and it takes a long time. It's a very slow process. Tank heaters, things like that, will help speed that process up, get that refrigerant to flash faster, and get that out of there. And what that does leave you with is all of that oil that stays in the cylinder. It's got to be dealt with in some way at that point. So the way I've always done that kind of thing is we'll just tip the cylinder over when we're done, and drain that whatever is in there into a bucket or a container of some kind and dispose of it accordingly. So that is just one method or one way of trying to mitigate that. So if you have a system that is, say you've migrated and you've got a lot of oil in that refrigerant, that's an effective way of separating that refrigerant from the oil. Hey, Mechanical Environments, I see y'all in the chat, guys. Hope y'all are having a good day. After compressor burnout. So if you've got a compressor burnout, you're not going to, in my training, you're not going to reuse that oil. That oil is, or that refrigerant, I mean. So at that point, it's not even a matter of concern. You're going to take that refrigerant out. You're going to take that oil out. That refrigerant is already contaminated at that point, and it is not worth the risk of putting back into your chiller. Now, the customer may have a different opinion on that, and in those situations, I offer no warranties. Like if they're gonna take that path and they're not gonna allow me to put clean refrigerant in there after a burnout, which has a high risk of future failures and is not easy to clean those systems up, I'm not gonna trust that refrigerant. So if that's their demand and they're not willing to make the budget to pay for a new refrigerant, then you get no warranty. And if you're not okay with that, then I'm sorry, go use a different vendor. I'm not taking that liability on. Um, Again, you being the tech, you may not have that much control of the situation. All you can do is make your recommendations, and if they're not followed, like these are things to keep track of, because I've known just POS managers who will turn around and use that against you later. Be like, listen, dude, I said not to do this. Again, if you get a manager like that, there's a lot of companies that have good managers. Okay, I would really consider just finding a better company at that stage. But that's up to you. That's your life situation. I can't live that for you. But that's how I personally have handled it. And I've got strong opinions there. So I'll just leave it at that. But I wouldn't be worried about it with a burnout. I'm just going to use new refrigerant to begin with and move on. It is well separation. That's per case reuse. All logged heat exchanger unit would rather replace oil or add after. Okay, let's get this one loaded in here. It's kind of a longer one, so just give me a second. Great questions, guys. Keep them coming. Okay? Doing really good. All right. Oil separation that's per case in use. Reuse refrigerant if oil logged heat exchanger. Usually would rather replace oil or add after. So I personally would much rather replace that oil. If I have to, whatever oil amount it was, while it could literally be majority of your oil charge, ideally it wouldn't be. But let's give an example of a situation like this. An RTHD, those are horrid at oil migration, and so it's a water cooled screw chiller, and if the machine isn't online and I can't do I can't get the compressor running to recover that oil first, and that means that all I have is just in the evaporator and it's stuck there. I'm going to go through that procedure I talked about earlier. Recover the system down. Try my best to judge getting the worst of the oil latent refrigerant, which is going to be on top, into a specific cylinder. And so from there, I can try to boil that refrigerant back out of that oil, get the refrigerant back, but I'm not going to try to go through the process of re-putting that oil back into the system. I would much rather just add fresh oil for whatever oil was lost. That is my personal preference in that situation. Now, if you can get the machine online, even if just for a short time, try to get some of that oil back. So a way to do that, if you were in a situation where you had a severe migration event, the way that I've done it, I'll add just enough oil into the sump to allow the machine to come online safely. So, I mean, just enough oil. And once you get it online, the oil recovery system, whether it be adductors with an RTHD, it's a gas pump assembly, whatever system they're using to recover that oil back. In a YCIV example, there's no oil recovery mechanism, but those will still stack oil in the evaporator and it can migrate there. At that point, like in those it just needs to run, right? We just need to get that compressor to run. Even if we can get 20, 30 minutes, it may not get everything, but we'll get a pretty good portion depending on the type of recovery that they have, the oil recovery. I mean, you'll get a pretty good amount of that oil back where it needs to be, whether in the sump, the oil separator, whatever the case. So on some of these, it doesn't take very long, and I would do my best, even if it wasn't completely safe for the machine. But I knew that I could make it run for a short time. Like, I would try. Now, that's me. And that also is very situational. There's some points that it's just not an option. You've got to be able to determine that. You, as the technician on site, have to make that call. But, yeah, I wouldn't, to answer very specifically, I wouldn't bother trying to put that oil back in. I would just trash it and move on to putting fresh in, getting the machine back online. Brace plate recovery rigs calcify. Let's go here. Okay. So, do brace plate recovery rigs calcify connected to tap water? Yes, they can. They absolutely can. Now, what helps us here is there's two things. One, we're only running water through it for a short period of time. And now I live in an area where I've got some pretty hard water, and like here in my house, we live off of a well, but we're not connected to city or grid water, so we're out here, and we have a very high calcium count, or parts per million, whatever the case may be, in our well water. And even then, it takes quite a bit of time of just slow growth buildup of that calcification before it even becomes noticeable, much less a problem. It's not a fast thing. So with using a brace plate for recovery as a subcooler, I'm assuming that's the direction you're going with that, then you're not moving that much water through it all the time. Now, one of the recommendations I've seen, and I see, so Jason Johnson, if anybody knows him, he has one of his own. He built his own brace plate subcooler. And one of his practices I've heard him talk about, and I didn't really do this for myself, I just didn't take the time to bother, but he likes to blow it out with some nitrogen when he's done and get all that water out of there, which most of the time it should help with a lot of that, move a lot of that water and the deposits out. Because, like, the issue with my method of just kind of letting it dry out on its own, maybe shake it a little bit, is those heavy water deposits that stay in there. Well, the deposit gets left behind after the water evaporates. So if you wanted to mitigate that, using something like nitrogen to purge that heat exchanger out would be a very effective method of trying to extend your heat exchanger's life. But I've used mine, and we've got really hard water, even in the city of Austin and San Antonio. Like, we've got some pretty freaking hard water here, and lots of, I mean, heck, I've had that 6 years, 7 years, something like that. It's been perfectly fine. I've not had that issue. So now you may have different water, you probably do, but I'm happy with the life I got out of mine. And if I had to replace it because it calcified up after so many years of usage, I think I'm okay with that as just a wear and tear myself. Anyway, good question. So the water call, nitrogen blowout. Yeah, nitrogen blowout after use. Okay. All right, we got a little bit more time. I am open to take some more questions. We've talked a lot about recovery. We haven't had an evacuation question yet, which is okay. Makes me wonder if we should keep this one focused on recovery and maybe do an evacuation separately. I can do some more polling around that. We can make that decision later. Yeah. Anybody has another question, feel free to get it in there. I'll take a second to kind of talk about for everybody that's in the in Chiller Academy, be having a look out the internal opening for the the service program, the service training program. I'm gonna be sending out some emails on that very soon. So if you're interested in participating or doing anything on the service training side with me, just be looking for that. The public stuff will go live sometime in April, but in the next week or so, everybody in the academy, you're going to start seeing some different emails come out to discuss that. So if you want to start that conversation early or touch base with me, feel free to reach out, and we can do that. How you doing, Jason? I see you in there, Bubba. And Froggy, I've seen you chatting here and there, bud. I just yeah, we've been hitting it up. Got to get to work, Sly. Yeah. Oh, see, not a question, but we had an air cooled chiller whose blew its high temp freeze plug due to a failed fan. We plan to replace the receiver. Anyone resoldered that plug? I don't know. No, what I mean by no is don't try to resolder that. So those, at least, how about this? The training I have on the pressure relief plugs, they're not using just a generic solder. They are using a specific blend of the alloy, if I'm not mistaken, and it's in there in just the right way. Like it's a process that they do as a safety device that they have to put that cap in, if you will. So I do not recommend using just our standard off the shelf solder because that is not the same, and it will not melt, because that the solder filler they have in there is designed to melt at a very specific temperature that is supposed to prevent a complete blowout. And what we have is meant for more of like actual line connections, like holding couplings together to where it doesn't blow out. And with a lot of our solders we have on the shelf, that it'll make a hold strong enough to where you'll burst the pipe before you burst the joint. So I don't recommend that. Just replace the receiver. Yeah, the fuse. Yeah, replace the receiver, please. I don't want to see anybody get hurt. Center pressure test. What you working on, Jason? What's your model? Okay. One of the things I thought I would talk about is a series setup like this. And I actually posted about this I guess a few weeks ago, and it created some very interesting conversations. So what I'm doing here is I am moving, or I'm doing a push-pull recovery or charging to get all of these cylinders in here. Now, one thing comes up is, well, hey, why didn't you use a good big 1,000-pound cylinder or something like that? Well, actually, this particular case, this machine had gone almost flat. I think we got 200 pounds out of what's supposed to be 1,500 out of the chiller at the time. And this is what the refrigerant supplier could ship us. They shipped us all these blue cylinders on a pallet, and then we just rolled them into the plant and began charging. And so this cylinder here, which is we were using 240s at the time, so 240 pound. These are 125s. So this is what we put the little bit of refrigerant that was there into. So basically what I've done is to speed up the process. Instead of having to hook and unhook, hook and unhook, hook and unhook every single tank, we just ran them all in series together. Now this is for charging specifically. So I'm pushing out of the recovery into the vapor of this tank, coming out of its liquid line into the vapor of the next tank, and then out of that liquid line into the next tank's vapor, out of liquid into vapor, and doing it all the way through until the final tank we're coming out of its liquid line and into the chiller. So what is happening is I'm pulling the vapor off of the chiller that's been of the refrigerant that's been charged, and I'm pushing that vapor specifically back into this cylinder. As I do that, it pressurizes the cylinder and pushes that liquid down. And as that liquid pushes down, it draws it into the next tank. Now you also have to keep in mind that because I am pulling vapor off of this chiller, there's also a little bit of a pulling action. So more than just it pushing, there's also some pulling. Those two in combination literally pushed all that liquid refrigerant through each tank all the way through until we had completely charged every tank with just one hookup. Now this takes a lot of hoses. That's one of the reasons why some of these hoses are just the small version. We just didn't have enough of larger hoses to do the entire thing, but we just wanted to see how far could we push this at the time. I was very curious. We had a bunch of tanks and we had just enough hoses to literally get every single tank connected. And so we just figured, what the hell, why not try? And it worked out beautifully. Now, in trying to do this for recovery, now again, I'm charging here, and I'm also doing a push-pull method. Trying to do this for charging, there's a couple of lines of thought, and I want to be very careful here because I don't want anybody to get hurt. One of the things I've been brought up with is that we have the 80% charging rule, but that's a DOT standard for if we're going to transport cylinders. It's also important that, like, if that cylinder is going to be out in a open climate where the climate is constantly shifting pressure and temperature, or not pressure, but constantly shifting temperatures heavily, we got major temperature swings, which is going to cause that tank to see pressure increase. Then we want to respect that 80% rule, period. But in a centrifugal plant, most of the time we have a very stable, not always, some of them aren't conditioned whatsoever. This particular one's down in a basement. So we have a pretty stable environment. And in that environment, I personally have had it to where during a recovery phase, filling a cylinder to its full capacity has not been an issue. Now, I'll only do it in that specific environment. And one of the methods I was taught before we would even use a scale, we'd put a sight glass on the leaving side, on the vapor side of our recovery cylinder doing the push-pull. And when we began to see liquid coming out of the vapor port, we knew that tank was full, stop it, move to the next cylinder. And that is a very standard practice for what I came up with. Now, there are some risks to that, and that's something you just have to understand if you're going to try a series hookup like that. You have to pay attention to what your plant conditions are, because I wouldn't do that if I knew that I was going to have major temperature swings. And there is still a risk that you fill a cylinder completely with liquid and it doesn't have any room for expanding and breathing of that liquid refrigerant. It's just going to be further compression. You could burst the safety disc on that cylinder, on a cylinder, very easily. So I want you to please just be careful with that. And that's one of the struggles we have sometimes is you'll see other people doing things. and even with myself, I don't always, it's not easy to always account for all the unspoken things. And that's one of the things I'm trying to solve with Chiller Academy is take as many of those unspokens that are just kind of things we know that we've learned and picked up along the way or somebody has passingly shared, and then put all that unspoken information somewhere where it's accessible, right? Has been one of my objectives. And this is one of those cases where you'll see me present something like, hey, let's do a series setup and we'll do all this on the recovery. And then, like, yeah, we're filling every tank technically completely full. We're not within DOT regulation. We're outside of, so if we wanted to transport these cylinders after doing this, we can't do that. We are not road legal. We would have to go through the process of moving that refrigerant elsewhere to get it into a road legal condition. So you'll see that option presented, and then it's very easy for us to sometimes forget. But I'm only going to do this in this particular scenario because of this, right? And I'm not going to do this in that scenario because the conditions changed and there is fluctuations and variability, and I don't want to create a problem. But we don't always take the time to explain that. So I wanted to lay that out here as one of the factors to understand. Okay, so yeah, if you see a setup like this, like I am specifically charging here, and I have done recoveries this way, but I am in a controlled climate plant. I am not out I'm not going to be transporting these cylinders when I'm done. They're going to stay here until I'm ready to use them again. And they're going to see about 75 degrees pretty consistently, give or take a couple of degrees. In that situation, technically, there's not going to be any failures. There's not going to be any the risk is, in my opinion, minimized. That doesn't make it right. So that's one of the things we have to also be mindful of, is sometimes these are things that we'll do because we feel that they're shortcuts we're comfortable taking, but that doesn't make them the right thing to do. And doesn't make them the by the book thing to do, which means that there is more risk in following that path. The chances of something going wrong are far higher if you don't do it correctly, versus the by the book, for the most part, will probably keep you the safest with least amount of risk. I'll say it that way. It's also going to keep you out of legal trouble, right? So that's the other thing of this. We have the liability aspect to the whole thing of what procedures we choose to follow. You choose the wrong path, something happens, you are liable, or your company is liable, either way, depending on your circumstances. And so things to think about, and I did want to take a moment to clarify that here. Again, if somebody has a question, feel free to shoot it out there. We're here to have a chat. We still got some time on the clock. That being said, there is another thing I want to follow up on that I, in the last, let's see, yeah, in 2 streams ago, we were talking about centrifugal discharge superheat. So one of the things I had talked about was how the discharge superheat will fluctuate based off of the load on the chiller. And I do need to make a correction here. So I am very used to working on variable speed machines, and so when I think through stuff at this point, I'm thinking through it from a variable speed capacity. So the discharge superheat on a variable speed will fluctuate and reduce and raise and such like I described previously, where it changes with the load, and we can reduce discharge superheat with load. Um, and there are some circumstances, though, that with a full load at peak, we'll see that discharge superheat kind of come down some just because of how the refrigerant flow characteristics are at the time, and the superheat, if I'm cautious to say that, coming off the evaporator, because we do have some level of superheat. Like, it's not literally no superheat. It's just such, like, it's only 1 or 2 degrees. So it's so low that it's not really measurable accurately with our standard equipment. So, um, yeah, we with a variable speed, you will see more of that discharge superheat fluctuations. And just to clarify, discharge superheat is your discharge temperature from your condenser saturation temperature. The difference between those is your discharge superheat coming off of your centrifugal. And that is the primary way that we will judge a centrifugal's, say, superheat performance. We won't base it off of suction superheat most of the time. There are some exceptions. Most of the time, we're going to base it off of the discharge superheat specifically. Most machines will run 15 to 25 degrees, 30 degrees of discharge superheat, depending on the load conditions. Some of them will get as low as 10 degrees and it still be considered perfectly normal. Now, the correction I need to make, that changes with a constant speed machine. And this was not something I've had previously connected the dots on. So there were a handful of guys in the community that reached out. We had some discussions around this. They also shared some material. I appreciate the feedback. Definitely not perfect. And so it helps me better present this information. So let me explain constant speed discharge superheat here while we've got a moment. With constant speed, that motor doesn't change. That's the whole point behind the constant speed. But there's still the fact that that impeller is spinning. We have a specific amount of heat from friction constantly being generated. So that because we can't slow the compressor down, we can't reduce the amount of heat that the impeller is generating just from rotation on its own. So what ends up happening is, as we unload the machine and we move less refrigerant into the impeller, because keep in mind, these are suction cooled compressors. There are some that use some liquid injection, but for the most part, majority of these are going to be suction cooled. Of course, then we could get into turbo core, and I could get off on a tangent there. Either way, the compressor itself, the impellers, are cooled by the suction gas. So as we unload and we move less suction gas through the impeller, we're not able to cool that impeller as much, which raises the discharge superheat that we have to have, because that each molecule of refrigerant has to take in more of that heat in order to properly keep the compressor from overheating. So less refrigerant means it has a harder time cooling the impeller that's running at a single speed. Most of the time it's going to be 3,600 RPM, or, well, I'm not going to say that. Ignore the RPM part. I'm sorry. Anyway, we're moving at a single speed, and so the discharge superheat will rise and increase in that scenario. So with less load on the compressor, higher discharge superheat. As the compressor loads up, and all else being considered proper, your flows are good, your refrigerant charge is good, your set points are good, all of that being correct, you will actually see your discharge superheat lower as the compressor loads up, because we're feeding more total volume into the compressor. That is what that is a very clear distinction between what you might experience with a variable speed and what you'll see with a constant speed. So with a constant speed, seeing a high discharge superheat at low load conditions is actually normal. But you should see that discharge superheat begin to come down as the load increases. So that is a correction. That is something that when I explained it previously, the way I approached it applied for variable speed machines. And that was the mindset I had when I was presenting the information, but I did not take into account, nor did I fully grasp a constant speed machine and how it doesn't follow the same discharge superheat curve that a variable speed does. And those it is because of how much refrigerant we are moving through there at a specific speed. So because the compressor cannot slow down, we're still generating just as much heat from operation, but we're not giving it as much cooling through the suction gas. I'm happy to answer any further questions on that if anybody has any. But I wanted to clarify that here, and then that whole snip I'll post separately later. So just, yeah, if you are working on a constant speed, I don't want what I previously explained to really screw up your troubleshooting process, because I was thinking about variable speed, because the vast majority of what we work on nowadays, at least from my side of it, like the vast majority of what I see, it's all variable speed, has been for a lot of years. There's not that many constant speeds floating around out there anymore that I see, right? That's me, my specific area, what we've got. That's not true for everybody. Anyway, last call for questions. Last call. Hope everyone has a really good week. I am very excited about launching this service course. And one of the ways that I'm doing it, just kind of talk about it some more. I'm just kind of I'm sharing thoughts because I do want to receive as much feedback on it as I can, and kind of the mentality I have around building it. And the advisory team I've put together for building that course, I really appreciate you guys. You have been instrumental in helping me work through that. So I've got a team of advisors that I put together. These are high-level senior managers across the United States, working at various mechanical groups. And part of what we're doing in there is we're discussing, okay, there's 3, 4, 5 ways of doing this particular thing. What is the safest and most effective way to accomplish this? Like, what if we're going to create a standard, what would our standard be? What would all of us want our technicians to do? That's been the thought process. Or in some cases not do. And let's specify that. Don't do this. Again, those unspoken things, putting those unspoken things down on paper that, say, the factory guidelines aren't going to explain. They expect you to already kind of know that. So they're not going to break it down on that level. So one of my ideas is I'm going to launch the training program, with a pretty decent library already started, but it's intentionally not going to be 100% complete. Not every single procedure and thing we need to do is going to be in there on purpose. The reason for that is I'm building what I feel are the, say, minimum basics of what you're going to need on a routine and what you might want help guiding through. Because keep in mind, these are step-by-step guides. These are step 1, do X. Step 2, do Y. Step 3, do Z. And there's a lot of notes in between on what you should or shouldn't see, and things to take into consideration. So that is the approach behind the training program. So the thought process is, okay, whatever isn't here, let's make it a request basis. So part of my idea is we can quickly create a procedure based on requests. So if we get several people asking for a particular procedure, we can get that in there quickly. That's not going to be hard. So if you know you've got a job coming up that you uh, need a procedure for, or that would help you guide through that work, then you can do that. And you, yeah. So I'm just curious as to some thoughts around that, and making it a like building a basic library and then making the rest a request basis and continuing to add on to the library so to help you get better training that you can actually apply, like things you can physically apply to your day-to-day work. That is kind of the goal and the thought process behind it. Um, yeah, so any thoughts on that would be appreciated. Um, let's see. Yeah, I'm really excited about it. I really am. I think it's going to be pretty freaking cool if you ask me. Granted, I mean, I'm only slightly biased, but I'm very proud of the work we're doing. Um, and it's created some very interesting conversations as we've discussed some of these things because there isn't a standard for even for some just really basic things. Like there's not it is recommended to do it this way. That doesn't exist. Not the way you not to the level you would think it would, right? If when you go through just the years of hands-on and then you sit down and you talk with a group of people that are on a national scale, very different backgrounds and training, and then some of the different perspectives and answers that come through that, and just the various literatures that get chunked around to try to back up different theories. Like it's fascinating the conversations we're getting to have to try to hash this out so that we can have a set standard, something that is actionable. And the course will have all the same features that the certification course has. Like you'll have a comment section on each procedure. So if you want more specific questions, you'll have access to the internal chiller community as well. So you'll be able to go in there and um, uh, post your pictures, post your questions, videos. We can have discussions around what you're seeing and what procedure you're trying to follow in the field, and have a more in-depth conversation inside of the community. So those things are all still just a part of the basic benefits of being in the program. So anyway, I feel like I'm kind of rambling now. Let's see. I can cosign. Almost everything is on a drive. Yeah, it really is. It's just, yeah. I mean, we knew this a long time ago. Drives, that's one of the reasons I took the time to really study and begin to get comfortable with drive theory, and then later the mag bearing technology, because it was just obvious that they're going to push this for a variety of reasons. They're going to push this. So fast forward, 10 years, and here we are. Literally everything has a drive on it. Like you have to special order the non-drive version at this point. Let's see. Yeah, and I appreciate the feedback, everybody. It does really help. Yeah, I appreciate it, Jason. Now, y'all are good people. It's been a crazy, it's been 7 years of all this, and a lot of you have truly been there for the majority of it, and I really appreciate that support and that feedback. I get to live my dream right now. Like this is my dream. I could not imagine from a work perspective getting to do something better than this. I'm literally creating the very things that I wish I had when I was trying to learn this stuff on equipment that I absolutely adore. Like, I live and breathe and bleed chillers. Like, this excites me. Every aspect of all this, air cooled, water cooled, doesn't matter. Like, I absolutely love this. And so then to be able to have an opportunity to make a living off of just doing this, and doing this in a way that I feel is better than what I see as the alternatives, right? Like, having the ability of truly creating something I think will help you more than those. That is just, this has been the coolest thing ever. And I appreciate all of your support, because without that, this wouldn't be real. This wouldn't be happening. I wouldn't be able to sit here right now. I'd still be with a wrench in hand somewhere, and that's about as far as I'd get with it. So, thank you for allowing this to be possible. Yes, yeah, a lot comes from improvising. That's the thing, it goes back to the unspoken. Um, uh, a lot of the little things that we think about and we do or don't do, and all those, there's a lot of little decisions we make, especially once we get experienced, that younger guys that are trying to learn, just they haven't had to make those decisions, so they don't, that those little improvisions just don't connect the same, because they haven't had to live through that. And I really think it's been one of my things that I wasn't conscious of it for a really long time, like a really long time. And I don't think the majority of people, as we gain experience, I don't think it's not an intentional thing, but we're just not conscious of how much of those little improvisions, if that's a word, I'm just gonna go with it is. There's a lot of those that we just don't even realize are there. Things we just figured out on our own. Um, but then being conscious of that and being able to communicate that to somebody who's trying to grasp it, um, I see how important that is and how much of a struggle that creates, and why there's sometimes so much frustration between apprentice and senior. This being able to translate all of those little unspokens is not easy. Like, it's really difficult to process through. Well, why do I feel that way? Why do I choose that path? Why go on X instead of Y? And it's all of those little things that you've had to deal with 1,000 freaking times that just drive you nuts, that makes you know better, and why you choose to take that path. It's not an easy thing. So I don't know. Anyway, getting all philosophical. A lot of it comes down to, well, let's not do yeah, exactly. Let's not do that again. All the times. Oh man. Oh man, all the times. Some Yeah. There's some great stories I'd love to tell one day, but I don't know that the safety standard, um uh I don't want people to get a phone call yeah, some of the stuff we get into, guys. It is ridiculous. Really appreciate what you've done to put together. Yeah, that's good. That's what a lot of this is for. Um, if you're not improving, like, here's the thing. Here's a very interesting concept that I heard a few months back, and it has really, really set with me. Um, when it gets to the point where it feels boring, right? Like, I've heard this 100 times, or I've seen this expressed this way. I've done this, has done that. It just, the content starts to seem almost dull, if that makes sense. Because it doesn't have the same newness and excitement. Oh, I haven't heard this before. Oh, yeah, 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 right? When it starts to get to that point with people you learn from, that's actually a good thing, because that means that what they've been trying to teach you is starting to make sense, and it's starting to set itself in, um, and you're solidifying it. So now the information doesn't have some of that same shininess to it. And I've had people that I've followed like on social media and stuff for different reasons, that at one time like they couldn't make anything bad. Just every freaking thing they came out with was the coolest freaking stuff. And then like as you learn and apply and start doing the things, it gets to where it's like, man, this is just, it's kind of repetitive. It's kind of just getting old. And then to realize that, okay, well then they accomplished their mission. If their mission was to not just entertain, but to help me learn how to do something better and improve myself, and they're still on that same mission, but I have continued my journey through their help, then they were successful. And I want that to be something similar here. I want to help you get to the point where I feel boring. Because if I feel boring with what I'm trying to talk about, then I hope it is because together we've gotten to a point where you no longer necessarily need everything I'm saying. And now you're able to stand on your own in a whole new way. And it happens slowly over time. It doesn't happen, like, it's not fast. So yeah, I hope that that is true, and that at some point my like the conversations like this don't benefit you the same way anymore. And I hope it's because, not because I changed what I'm talking about. I hope that's not true. But I hope it's because you just no longer need to hear it anymore. And at that point, good job. I think that should be the goal, in my opinion. Anyway, we're going to wrap this up. I hope everybody has a wonderful week. Thank you for sharing your experience. By catch your philosophy. Uzbekistan. I hope I said that right. Pronunciation is not my strong suit, but I appreciate you joining in. And hey, if you're able to follow me and the way I talk, then your English isn't as bad as you probably think it is. I'm just going to say that now. Yeah, I'm not the most crystal clear speaker in the world, but either way, everybody stay safe. MTT, make the time for your family, for your spouse, for your kids. This is a tough industry. They really need you. If we don't make that time, if we don't put that effort in, it's not going to be there. It has to be a conscious effort. I've made my own mistakes on that front. I really would rather you not have